Dear students, after watching this video, you'll be able to solve questions like this asked in GATE Aerospace exam for 2 marks very easy. So let's start. Now, when I was in college, I was really scared of these topics like material derivative, local derivative, convective derivative. But today, we'll learn it in such a way that these terms will never be a problem for you. And we will solve the GATE question very easy. So to solve the question that you have seen, first we have to understand what is Lagrangian and Eulerian description. Now, all of you must have studied projectile motion when you were in college, isn't it? Now, projectile motion is something which all of you study. Now, when we are studying projectile motion, what are the things that we calculate, right? What are the things that are of importance to us, right? It is the initial velocity, right, in both the directions. What is the maximum height the ball reaches, right? What is the range, right? What is the time taken for the total flight, right? What is the velocity of the ball when it is about to land? So in all these things, one thing is common, that we are following the particle. For example, here it is the it is the basketball. So every time what we are doing, we are concentrating on the basketball. What is the maximum height of the basketball, right? What is the velocity of the basketball when it enters the basket? What is the range it has flown? Each and everything. So when you concentrate on a particle and try to find out the properties of that particle throughout its travel time, that is the Lagrangian. And generally in mechanics, be it solid mechanics or engineering mechanics, right, everything is defined in the Lagrangian description. For example, if you use the Newton's second law of motion, F is equal to ma, this is the Lagrangian description. Means basically what we are trying to do is we are trying to find out what is the force on the ball at each moment of time, right? At each different point of time. And to that, you have to find out the acceleration at different point of time. So in Lagrangian description, what we do, we track a single particle or a body, right? And monitor what is its position, what is its velocity, what is its acceleration, and what are different properties of that part. Now imagine you have to apply the same concept to fluid mechanics. Suppose you have to find out what are the forces on the particles, right? The fluid particles flowing over an aircraft. Or what is the force the fluid particles are applying on the aircraft. For that, you have to track billions of particles, and that will simply become a nightmare, right? If you have to track so many different particles. So here comes the other approach, that is the Eulerian approach, where instead of tracking each and every particle, what we do, we define a control volume. And instead of just roaming around tracking the particle, we stay fixed, right? Our X, Y, Z coordinates are fixed, and simply what we do, we track all the particles that are coming into the control volume and going out of the control. This analysis makes fluid mechanics very easy. So what we do, we specify the coordinates X, Y, Z, and then try to figure out the properties of the everything that is coming into the control volume, like the velocity, pressure, temperature, whatever it is. And this kind of description is known as the Eulerian description, where we have a fixed window in space called the control volume. Now let us try to understand this even more, right? So in Eulerian approach, for example, suppose a team of 5 is playing a basketball. Every one of them has a ball in their hand. Now each one of them throws the ball into the basket, right? So instead of monitoring how the ball is traveling from someone's hand into the basket, what we will do, we will take the basket, right, as our control volume, and instead of following the ball from the hand to the basket, we'll simply focus on how are the properties of the ball when it is actually getting into the basket. So we are going to just concentrate on this portion. How are the balls, what is the velocity of the balls getting into the basket, right? What is the angle might be, what is the acceleration of the ball getting into the baskets, right? So we are just concentrated on this volume. So this approach is basically the Eulerian approach. Now don't worry, we will have even more examples, right, to understand this, right? But the problem that we have at this point of time is not that Lagrangian or Eulerian description, right, understanding. The problem is that most of the mechanics have been described in the Lagrangian form. Now if you have to use it in the Eulerian form, now this is a difficult. How to do it, right? As I said, F is equal to ma, Newton's law of motion. It is described in the Lagrangian form, right? Because m is the mass of a particle, right? A is the acceleration of the particle, F is the force on that particle. So we are tracking it throughout. Now here, the material derivative comes into picture. It is a material derivative that helps us bridge the gap between Lagrangian and Eulerian. Basically, the material derivative, it transforms something written in the Lagrangian description into Eulerian. You'll ask how. Now, this is what the formula, the derivative formula looks like. Del d by dt is equal to, don't be scared, partial derivative with respect to time plus velocity del into that property. Now you'll say, so what kind of formula is this? It is completely going out of my mind. Don't worry, I'll explain it. So let us consider any property eta. Let us consider any property, let me say eta, right? So this eta could be pressure, it could be temperature, it could be velocity, it could be acceleration, whatever it is, right? So using this, we'll try to figure out how the Lagrangian description is actually converted into Eulerian description, right? Don't worry, we are going to understand in detail. You might be a little bit confused at this point of time, but all your confusion will be clear as you go through this. So we are going to substitute this eta here. So if you substitute the value of eta here, so it simply becomes something like this, d eta by dt. Now you'll say, so why we are writing it in capital letters? Don't worry, you will understand it in some time. Del eta by del t plus v dot del operator into e. Okay, so you'll say, so I still don't understand it. Don't worry, we are going to now get into more depth to make it very simple for you. Now you look at this first of all. Okay? So what is del? So if I am taking the del operator, it simply means this is how the del operator is written. Partial derivative with respect to x plus del by del y j cap plus del by del z by k cap. Now if you multiply eta with it, so del eta will become something like this, del eta by del x I cap, right, plus del eta by del y j cap plus del eta by del z k cap. Now if you dot product it with velocity, we know what is velocity. The velocity is written like this. It will be u, just hold on, yeah, so it is u I cap plus, so u is the component of velocity in x direction, v j cap plus w k cap, where v is the component of velocity in y direction, w is the component of velocity in z direction. Now if you make a dot product, okay, if you get a dot product, v dot, right, del eta, so this is how it will look like, u del eta by del x. Don't worry, we will simplify it even more for you to understand. Del eta, all of you, I hope that you know what is the del operator and what is the dot product, del eta by del z, right? So now if you expand this formula, this is how the formula is going to look like. So d eta by dt is nothing else but del eta by del t. Don't worry, we are going to understand each and everything. I'm just expanding it for you. Change of eta with respect in the x direction with velocity in x direction plus change of eta in y direction, right, with velocity in y direction, change of eta in z direction with velocity in. So this is how the operator looks like. Now try to understand what are the individual terms represent. This term is nothing else, it is simply the rate of change of eta. So whenever we write it this way, it is similar to this, d eta by differentiation of eta with respect to time, right? Differentiation of eta with respect to time, right? Now this is the Lagrangian approach. For example, if we replace eta with velocity, it will simply become dv by dt. What is dv by dt? That is nothing else but acceleration a of the particle. Right? This is partial derivative of eta with respect to time, right? Means what we have done here, we have kept x, y, z as constant, right? Here it is not so. Here it is not x, y, z are not constant, right? We are moving along with the particle. Here x, y, z are constant, right? Don't worry, we are going to use velocity as an example and we'll see, right? And this is, what is this? This is the variation of eta with respect to space. Variation of eta with respect to space. Now, if you combine all of this, okay, we are going to understand it. This is known as the material derivative. This is known as the local derivative, and this is known as the convective derivative, right? So, what are the terms representing? You see, material derivative is nothing else but the Lagrangian form, right? Now, why we are writing a capital D here? Why you are not writing small d? Just to differentiate. So, the capital D, even if you write it this way in the small d, there is no difference. Simply, I am writing capital D so that I understand this is the material derivative. This is not simply you're differentiating eta with respect to time. This is actually representing the material or the total derivative. So you get to know that, okay, this operator is there, means we are trying to link the bridge Lagrangian and Eulerian approach. Right? What is local derivative? Local derivative is nothing else the partial derivative of the property with respect to time. Don't worry, we are going to take property velocity as the property and we are going to see it. Convective derivative is the variation of property with respect to space. Right? Local is variation with respect to time. at a particular space, and convective is variation of velocity with respect to space, keeping time constant. Okay, enough of this. Let us try to understand what is the material derivative of velocity. Now let us take velocity as an example, right? So velocity, as you have seen, we can write it as u I cap v j cap plus w k cap. Now when you are taking material derivative of velocity, right? So what does it mean? Why you have written velocity like this? For example, suppose it is a fluid, right? Let me take three coordinates here, x, y, and z, right? Let me say the fluid is flowing somewhere, something like this, right? So if you take out the velocity of the fluid at a point, okay, so it will have all three components. So u is the component in x direction, v is the component in y direction, and w is the component in z direction, right? Now if you want to write down it in material derivative, so we are going to write capital D v by capital T, right? This is equal to del v by del t plus v into del operator of. Now this is a vector. This is written in vector form, right? So while writing it, okay, I'll just try to answer you, show you what are the things. This is nothing else. This is known as the material derivative or material acceleration or the total acceleration. Total acceleration. Whenever you're using the formula F is equal to ma, right? This is the acceleration. This is how we calculate the acceleration. It's basically nothing else but dv by dt, right? This is known as the local acceleration, and this is known as the convective acceleration. We are going to resolve it, don't worry, and we are going to understand it fully. Convective acceleration. So basically, local acceleration, what is it representing is how the velocity is changing with time if we keep the x, y, z constant. And what is convective acceleration? How is the velocity changing with space if we keep the time constant? Okay, so there are two parts, as you have seen, local acceleration and convective acceleration. This represents how the velocity at a fixed point changes over time, and convective acceleration represents how a fluid particle accelerates as convected or moving through space. Let us take an example to understand this. Let me say we have a road, right? And there are few speed breakers in the road. These are speed breakers. And there are many cars which are coming on this road. There are many cars. Okay? Not just one car, there are many cars. There are cars, vans, buses, every different things coming on this road, right? So initially when they're coming in, let me say they're coming in a velocity of 60 km per hour. Now before the speed breaker, what will happen? Definitely they will apply the brakes. So before getting into the speed breakers, they apply brakes and the velocity reduces to 10 km per hour. And after the speed breakers are over, then again accelerate, right? And velocity increases to 60 km per hour, right? Now suppose you are sitting somewhere here, and watching it. You are relaxing and you are watching the car. So if you are watching the cars here, okay, so what you will see, the velocity change during this at any point of time. So you are simply going to see that, okay, the velocity of the cars are not changing with respect to time, right? We are just looking at this point, okay? So we have fixed the xyz coordinate, right? And you are simply seeing how the velocity is changing, right? Different cars are coming in. So you are simply seeing the velocity of each car with respect to time. Right? Your position is constant. Okay? How is the velocity of different cars when they are moving into the control volume? It is changing. Getting my point? Right? So see, different cars coming in. The first car comes in, you see the velocity, okay. The second car comes in, you see the velocity, okay. The third car comes in, you see the velocity, okay. So you see different velocities, right? Because some average velocity is 10, some car might be moving with 11, some might be moving with 9.5 km per hour. So you see there is a change in the velocities as even if you're concentrated on the space. So this is the local acceleration, right? Velocity at a fixed point changes over time, right? You have to understand we are not following one car, we are just concentrating on different cars coming in and going out, right? The first car comes in, what is the velocity? The second car comes in, what is the velocity? What is the change in velocity from the first car and the second car? Let me say the first car moves in 11 km per hour. The second car moves at 10 km per hour when it goes over the speed breaker. So you'll see there is a change in velocity with respect to time. So this is the local acceleration part. Now what is the convective acceleration part? Now if you take the whole space as one, take the whole space as one, then you will get to see initially the cars are moving at 60 kmph. They slowed down, means there was a deceleration here, and then after crossing the speed breaker they accelerated, right? Again they moved on to the 60 km per hour. So there is an acceleration. So if you take the space as a whole, you'll get to see that again with space, even if you take time as constant here, you will see that velocities were around 60 km per hour here at point A, then it changed to somewhere on an average of 10 km per hour at point B, then it went on to again 60 km per hour at point C. So you see over the space also there is some amount of acceleration in this the acceleration. That is known as the convective acceleration. As a whole, you must have understood at least one thing, right? Here we are not concentrating on a single car. We are concentrating on the group of cars because the cars are moving, coming inside the control volume, going out. So we are not fixed on one car. If it was a Lagrangian approach, we would have concentrated on one car. How is the car, the velocity of the car changing with time? That is the difference. So this is the Eulerian approach. And in fluid mechanics, it is very important to understand this before proceeding further. Now, once we have understood this, okay, let us go back to the equation that we have seen. Now, to understand this equation, okay, you see velocity is given as this. So there are three components of velocity, right? What is the u component of velocity? Can you see? The u component of velocity is 4t at I cap. What is the v component of velocity here? Minus 2t square y j cap. Okay, we need not write the I cap j cap because we are simply writing the u component and y component, right? It is very obvious that u component is in the x direction. So instead of, let us not confuse ourselves by writing the x I cap, j cap and k cap. And w component, that is the z component of velocity, is nothing else but 4xz, right? Now, if you really want to perform the material derivative, right, we will actually have three components. Okay, we'll have three components. Let us understand all three components. So first, we have already identified the velocity component, right? We have already identified the velocity components, as you have seen. So u is 40x, v is minus 2t square y, and w is, the first step is to identify the velocity components, 4xz, right? Now if you want to perform the material derivative here, we'll have to perform it separately for u component, y, v component, and w component. For example, okay, all of you try to see this. I will erase this and rewrite. Okay, so you see, if I want to write down what is the acceleration in x direction, acceleration in x direction is basically given by du by dt. This is the material derivative, right? So this is equal to partial derivative of u with respect to time plus change of u in x direction multiplied by velocity in x direction plus change of u in y direction plus multiplied by velocity in y direction plus change of u in z direction multiplied by velocity in z. Similarly, if you want to find out what is ay, acceleration in y direction, so it is dv by dt. This is the Lagrangian form. And if you want to write it in Eulerian form, right, so it is going to be del v by del t. This is the local acceleration. How is the y component of velocity changing with time, plus change of v in x direction multiplied by velocity in x direction, plus, you can remember the same way I am doing it, right? This is the easiest way to remember it. Change in velocity v in y direction multiplied by velocity in y direction plus change in velocity in z direction multiplied by velocity in z. Similarly, if you want to write az, how you are going to write it? It is basically capital D w by capital dt. So this is representing nothing else but rate of change of w with respect to time, the material derivative. This is equal to what? Partial derivative of w with respect to time, the local acceleration part, then rate of change of w with respect to x multiplied by velocity in x direction plus rate of change of w with respect to y, right, velocity in y direction plus rate of change of w with respect to z, velocity. So if you see this is the material derivative, material or total acceleration. This is the local acceleration part, right? And this is known as the convective acceleration, right? How is the velocity changing with space and how is the velocity changing with time? Now, the way I have written the formulas, if you try to memorize in the similar way, it is going to be very easy for you to understand. Having said that, let us compute the x component of acceleration, right? Let us compute, let me rewrite it for you, the x component of acceleration. Let me rewrite it for you, right? So ax, as you have seen, it is nothing else but partial derivative of u with respect to time. Again, let me repeat, you have to practice this multiple times. Rate of change of u with respect to x multiplied by the velocity in x direction plus rate of change of u in y multiplied by velocity in y direction plus rate of change of u in z plus multiplied by velocity in z direction, right? Now, what is u? U, we know it is 40x. We have already seen, right? What is v? V is minus 2t square y, right? And what is w? W is 4xz, right? So if you do del u by del t, the first term del u by del t, so it is coming out to be how much? 4x. If you do del u by del x, right, it is going to be 4t, this term. Similarly, if you do del u by del y, what will be del u by del y? What will be the value of del u by del y? Del u by del y, as you can see, u does not contain any y y term, it is going to be 0. Similarly, what will be del u by del z? Since the u term does not contain any z term, it is again going to be 0. Now, if you substitute these values in the acceleration part, so du by dt will simply become 4x, right? And u 4tx multiplied by how much? 40 plus 0 plus 0. So if you see this is nothing else but ax is equal to how much? 4x plus 16t square x. So this is the acceleration in x direction. This is the acceleration in x direction, and we are required to find out what is the acceleration, right, at point -1, 1, 0 as given in the equation, right, at time t is equal to 1. If you go back to the equation, if you look at the equation, this is where we need to find out the acceleration at. If you substitute the values, right, the value of acceleration, if you substitute the values, 4 into x, 4x means 4 into -1 plus 16 into 1 square into -1. So it is coming out to be -4 minus 16. So acceleration in x direction is going to be how much? -20. Similarly, we can calculate the y component of acceleration. Let us quickly do it. Right. So let us first write down the equation for velocity in y direction. Let us first write down the equation of velocity in y direction, right? So if I want to write down ay, so what is ay? First of all, change in velocity, change in v with respect to time, right? Del v by del t. Change in v with respect to in x direction multiplied by velocity in x direction plus change in velocity in y direction multiplied by velocity in y direction plus change in the velocity v in z direction, right? Multiplied by velocity in z direction. Let us rewrite the x, y, u, v, and w so that it becomes easy for us to compute. So u, we have already seen it is 4tx, right? We have seen v, it is equal to minus 2t square y. We have seen w, it is equal to plus 4xz. Right. Now, to calculate the first term is del v by del t. So if you partially differentiate v with respect to time, means we are keeping others constant. So you can see it is clearly, you can see if you differentiate with respect to time, right, it is going to be minus 4 ty. Let us differentiate velocity with respect to u. You can see there is no x term in v, so it becomes 0. Let us differentiate velocity with respect to y. If you differentiate it with respect to y, it is going to be minus 2t square, minus 2t square. And similarly, if you differentiate velocity v in the z direction, you're going to see if you differentiate this in z direction, because there is no z component, it is simply going to be 0. Now, if you substitute all these values in the ay equation, so this is going to be minus 4ty, right? This is going to be 0 because del v by del x is 0, right? We also know that last term is going to be 0, del v by del z is 0, right? And this term is going to be minus 2t square y, that is the v component, multiplied by del v by del y, that is minus 4ty, minus 4ty. Oh, sorry, it's not minus 4ty. It is, in fact, minus 2t square. My bad. Yeah, I corrected. Minus 2t square, right? This term. So it simplifies to something like this: minus 4ty plus 2 to the 4 t to the power 4 y plus 4 t to the power 4 y. Now we need to compute at -1, 1, 0, right, at time t is equal to 1. So if you substitute all these values, you will see that the value of ay is coming out to be 0. Substitute t is equal to 1, y is equal to 1, right? You will see minus 4 plus 4, that is equal to 0. So this is the component of velocity or component of acceleration in y direction. Similarly, let us calculate what is the component of velocity in z direction. Again, quickly we will write down what is the value of az. Az is actually, this is very important for you to practice it regularly, right? So del w by del t, so rate of change of w with respect to time, right? Then change in w in the x direction multiplied by velocity in x direction plus change in w with respect to y direction into velocity in y direction plus change in w with respect to z direction, right? Velocity in z direction. Now let us quickly write down what are the u, y, u, v, and w component. U is nothing else but 4tx, v is nothing else but minus 2t square y, and w is nothing else but plus 4xz, right? So if you say del w by del t, and if you differentiate it with respect to time, you'll see it is coming out to be 0 because there is no time t here. Right? Similarly, if you do del w by del x, if you differentiate with respect to x, so it is going to give you 4 times z. So what is del w by del y? It is going to give you 0 because there is no y component. Similarly, del w by, if you do del z, it is going to give you 4x. If you substitute all these values in the equation of az, so it is going to be 0 plus u, that is 4tx into 4z plus 0 plus the value of w is 4xz, right, into 4x. So if you see the component of velocity in z direction, so it is coming out to be 16txz. So 4 for the 16txz plus 4 for the 16x squared z. 16x squared z. So you see, if you've noticed it, right, the velocity, the acceleration is a function of 4 parameters: time, x, y, and z. Right? So x, y, z are the coordinates and t is the time. Now at -1, 1, 0 at time t is equal to 1. If you substitute all these values, you will see that az is coming out to be 0. So the z component of acceleration is also equal to 0. right? So once we have done this, let us write down the equation of acceleration. So if I now say what is the acceleration can be written as ax I cap plus ay j cap plus az, right, k cap. And we have seen that ax is nothing else but minus 20, right? This is 0 plus. Now if you want to find out what is the magnitude, so the magnitude is nothing else but root over what magnitude is being asked. So it is nothing else but ax square plus ay square plus az square. So this is equal to root over minus 20 square, right? Because ay and az are 0. So the magnitude of acceleration is coming out to be 20 meter per second square. So you see, we have been able to calculate the acceleration of the fluid particle, right, using the Eulerian description. It wouldn't have been possible to calculate the same using the Lagrangian method. So guys, I hope that you enjoyed this video. If you have any doubts, if you want me to clarify anything, if you have any confusion, please put it in the chat box, right? And at the same time, there is also a link provided in the chat box through which you will be able to join the GATE 2027 classroom, where you'll get free access to different materials, study materials and questions. Thank you. See you once again.